Last week we discussed about the anisotropy further and further, giving some examples of minerals. Okay, so another anisotropy that you can consider is the cleavage. Also, you can consider as an anisotropy of minerals or crystals, right? Because flat surfaces parallel to crystallographic planes we call cleavages, right? So you can see the cleavages in, for example, the calcite crystal, right? So the surfaces parallel to the crystallographic planes, these are the crystallographic planes you have, right? For calcite, for example, right? Uh, so you can find 120 cleavages parallel to these surfaces, right? So this is what we call a cleavage, right? It's a kind of a breaking surface. You can easily break the crystal in along these surfaces, right? So such surfaces are called cleavages. You can find these cleavages when you observe a mineral physically or under the microscope, right? So the along these cleavages, it's easy for the mineral to be broken, right? So that's what we mean by cleavage. It's one of the physical properties of crystals and also minerals. uh, but in glass, probably you may have observed when a glass is broken, right? When a glass is broken, you never see this type of systematic lines, right? For some crystals, you have this type of systematic lines like this, or even sometimes cross-cutting lines. In this case, 120-degree for calcite, you can see in between. For some minerals like pyroxenes, you will learn these things later on. You will see some cleavage like nearly 90. Okay, it's like 84 degree, right? So this type of cleavages are available, but for glass or even quartz, because glass is the amorphous form of quartz, right? Quartz is a U2. Amorphous form of quartz is glass, right? Both glass and quartz does not have this property. Instead, you see some kind of some circular type of fracture like thing, right? When you break quartz crystal or even a glass, right, in your window glass, for example, or when you travel by bus, you may have seen some edges of the window glass is broken. So there you will see some kind of some concentric pattern of kind of a fracture, right? So this is we call a fracture. In contrast to cleavage, fracture is not systematically distributed, right? It may be random, but in a shape like this, right? But cleavages are very systematic like this. Okay, right? So these properties are there. These are also anisotropic, right? They are not distributed evenly within the crystal. I mean, it depends on the direction. It depends on the direction. The distribution of these cleavages or fractures is also different, right? And also different deformation conditions in different directions of crystals. Deformation means you haven't learned it yet. Deformation means under the interior of the earth, right? When the rocks are at the depth, right? Below the surface, we have a lot of rocks, right? But actually, the rocks that you observe on the surface or near surface are uplifted rocks. Actually, they were at very deep depth levels some millions of years ago, right? Some 30 kilometers or 50 kilometers or even greater than that, right? Later on, gradually with the erosion of the upper layers of the rocks and then weathering and soil removal, this we call erosion. After result of erosion, these rocks are getting exposed to the surface gradually, right? This is what we call upliftment. Probably in the first semester, you may have learned under the earth processes, right? about this upliftment process, right? Exhumation or upliftment, right? Again, we will learn about these things later on, right? But for the time being, you can read the literature in the internet. You can just type isostasy, right? Isostasy, ISOSTACY, isostasy, and then you can understand about this entire process. Some rocks were maybe 100 kilometers below the Earth's surface, but after like 50 or 100 million years, or even 200 million years later, right? You will see these rocks on the surface. So today's rocks that you observe on the surface are there as a result of maybe 200, 300 million years of tectonic processes, right? Interior processes, dynamic processes of the Earth. Okay, right. So during this process, there are a lot of tectonic forces. We call some different types of forces. For example, due to the weight of overlying rock mass, right? We call it lithostatic pressure, right? Something like the hydrostatic pressure, right? You might observe this type of tectonic forces. So then the rocks get bent and sometimes fractured or moved, sheared, like that, right? So many processes are taking place at the interior of the crust, right? Because the temperatures and pressures are very high. Even though rock is a very solid body, they have the ability of kind of movements or flowing feature, something like a jelly, right? You can just remember jelly, which is not a liquid, and also it is not a solid also, right? So it has a semi-solid property. So rocks are also like that when they are residing at the interior of the Earth. So they can have different shapes. So that changing their geometrical shape is called deformation. So this deformation is also anisotropic feature, because in different directions, for example, this crystal can deform in a different way than when it being deformed in the other direction, right? So the applied force, the force exerted there will make its geometric shape in a different configuration depending on the direction, right? So that is also one thing. And also the hardness, even the hardness, right? The how hard the rock, how hard the mineral is, right? Mineral or the crystal is, right? We will learn about the hardness also under the Earth's materials. uh, in some different directions the hardness is also different, but in general there is a given hardness for a mineral most of the cases. But if the mineral is so anisotropic, then you will see uh, the properties changing in different amounts in different directions, right? So the hardness is actually the resistance to external resistance to the external stresses. Uh, and also the ability to be scratched, right? If you take one mineral and you want to scratch it with another mineral, the harder mineral will scratch the less harder one, uh, and you can see some scratch mark there. But the harder mineral, you don't see any scratch mark, right? So it's a relative property. So depending on that, we can see the hardness, how hardness varies, right? In some different directions, crystallographic directions, these are crystal faces. Okay, so different directions will have different hardnesses in some cases, but this is not always true for all the minerals. Remember, right? Because there is a defined hardness for a given mineral, but very slightly it can change depending on the direction. But I don't expect actually for all the minerals to change like this in a big scale, right? 6 to 7 here, 4 to 5 in the other direction, but it's very rare, right? Remember, it's not always changing, but very little changes, like 4 in one direction and the other direction 4.5, it might be. Okay, So this is kyanite hardness. This is the mineral kyanite hardness. Uh, Kyanite is a bladed type of crystal, right? We call it bladed type because you see the elongated direction of the crystal in this one direction. So therefore, this hardness considerably varies in kyanite. Okay. Okay, another feature that determines the anisotropy in crystals is birefringence, right? This birefringence is an optical property, right? This is an optical property. So what is optical property? The properties distinguishable as a result of the incident light or penetrating light through a crystal, right? So it's a light property, right? As a result of the incidence of light rays, right? Some crystals show different features. So these are optical properties. Under second year optical mineralogy course, you will learn in detail about the optical properties, right? So birefringence is one of those. Birefringence means due to refraction, internal refraction of the crystal, the light rays bend, and when it reaches through a special film called the polarizing film. This is a polarizing film, right? So it's something like a sunglass. Okay, in the microscope we have that, right? You will learn about the microscope and their configurations and apparatus, the accessories and all in under the optical mineralogy course in the second year, right? So the geological microscope we call a petrological microscope, which is different from a biological microscope, which you use for normal biological observations. Because in biological microscopes you don't have this polarizing film, right? In petrological microscopes, we have two polarization films so that we can see different properties of minerals uh, due to the polarization effect of the light rays when traveling through these microscopes. So actually the polarization effect means normal light ray has vibration directions, right? This is a electromagnetic radiation, right? Electromagnetic ray. So it has vibration directions in all the three-dimensional planes, right? The light particles or the rays vibrate in all directions. But when you put a polarizing film and let the light go through that, you can observe only one directional movement of the rays. Okay, so all the other vibration directions are cut by the polarization field, right? So this is what you call the polarization effect, and which is available in the sunglass also, right? So anyway, this polarization and also some other effects, some other optical effects produced uh, splitting of a light ray when it is traveling through a mineral or a crystal, right? So you can see here single ray is coming from this side, right? Only one ray is coming, but it's split into two rays. This is one and this is two. We term them as ordinary ray and extraordinary ray, depending on the refractive index, right? So you will learn details, but just for the time being, you can understand it's like this. And also sometimes it's called slow ray and fast ray, because one ray is fast than the other ray. That means there is some time lag also in between these two rays. In other words, one ray after splitting, one ray comes faster than the other. So when you see the ray going out from the mineral, one ray is faster, right? So there is some distance difference of traveling distance difference of these two rays, right? So anyway, this property is also different in different directions. Okay, so that is another anisotropic property of crystals. And we have another optical property that is what we call pleochroism. Pleochroism is resulted as a result of absorption of light by crystals, right? So in different directions of a crystal can absorb the wavelengths in different amounts, right? So in different absorption of light or differential absorption of light causes the mineral to change its colors when you rotate the mineral, because when you rotate the mineral only you can expose its different phases to the incident light, and you will see different shades of lights when it's rotated, right? For example, here light color, and here dark pink color, here light color, bluish color, like that, right? So it depends all on the mineral phases, right? Mineral phases means the crystallographic orientations of different phases of the crystal. Okay, so you see different rays are absorbed and different rays are allowed to travel through. So what is going out will give you the respective color, right? When it is absorbed, you don't see that color, right? If everything is absorbed, then you will see in which color? Black, right? So if something is black, means all the colors are absorbed by that material. Okay, so these pleochroism properties are also anisotropic, and sometimes it's called dichroism, trichroism, also in gemology, especially, right? But for geologists, it's okay. It's enough that you use the term pleochroism uh, as a general term to show the to indicate the differential absorption of light. All right. So these are anisotropic properties of minerals, and some another important anisotropic property you can see is again the optical properties. I mean the absorption of light, right? It's not just the pleochroism, but exactly the absorption. You can see some examples, right? For example, here you see this diagram. There is incident light here, right? This is the light coming into the material. So this is the material, right? So incident light can be reflected, right? Some rays can be reflected back, right? It won't go through the mineral, so nothing happens. But uh, some of the rays can be absorbed by the crystal itself, right? So then that particular wavelength, because the light can be split into different wavelengths, so some of the wavelengths can be absorbed. So those wavelengths you never see coming out from that particular material, right? Some rays, some wavelengths are allowed to transmit, right, out, and some are allowed to be scattered, right? I mean, in different directions. You can see they are moving after reflection, refraction, right? So, in the case of cadmium sulfide, it's also a crystal, right? It absorbs higher energy visible light, like blue, violet, like colors, right? So that means here this is higher energy range of the electromagnetic spectrum. Uh, that is, those are absorbed. So never you will see uh, blue or violet colors from this crystal. Instead, uh, the other wavelengths like red, orange, yellow, this range is transmitted, right? That is transmitted. But the other wavelengths like green, like these wavelengths are absorbed, so that you never see cadmium sulfide crystal in green colors, right? Usually you see the cadmium sulfide crystals in red, orange, or yellow color, because those are the wavelengths that are allowed to be transmitted. Another example is there, the sapphire, right? The corundum mineral, the gem minerals, the one of the very expensive gems Sri Lanka is famous for, right? Corundum or ruby sapphire, right? The blue, Ceylon blue is a sapphire, right? nilmanik can ratu kata nil kata කියලා කියන්නේ, right? those are those are the aluminum oxide, alumina, right? So the blue one is the most common one. It's sapphire, so you see them much in Sri Lanka. But when the sapphire crystal is mixed with some tiny amounts of chromium oxides, what happens? Normally, sapphire is colorless, and it causes uh, blue ray to be transmitted, right? But when you add, because some titanium is there, right, in sapphire. Otherwise, it's normal sapphire should be, corundum should be transparent and colorless, right? But when it contains some titanium-like thing, titanium oxide-like impurities, it can yield blue color, right? But when chromium is present, what happens? Chromium is present, uh, it absorbs these colors, blue, orange, yellow, green, like all the wavelengths are absorbed. This range is absorbed, right? From a longer range, right? From here to here is absorbed, okay? All these things are absorbed, but red is transmitted. Red is allowed to transmit like here, right? Red is transmitted, that means this one is transmitted. So now the sapphire is not no longer yellow, no longer blue, it's red, right? Then we call it ruby, right? So it's deep in red color. So that's how you see the red color in ruby, right? Otherwise, sapphire is normally colorless and transparent. And it can be blue when you have titanium and also ferric, right? Some ratio, some mixture. So the mixture of this titanium and ferric gives different shades of blue colors for the sapphire, because light, very light blue sapphires are there, intermediate blue sapphires are there, and deep blue sapphires are there. Sometimes you may have heard carcanil, the deep blue sapphire, right? So this depth depends on the wavelength of the transmitted light. Okay, so the ruby is also same. Sorry, ruby is also same. It gives out the red color, right? But this red color is also not isotropic, right? In crystal orientation, depending on the crystal orientation, you can see the strength of this color, right? And some magnetic and thermal properties are also anisotropic, right? It results different thermal expansion uh, coefficients, right? And thermal conductivity, right? For example, gypsum, right? They have different properties along different directions. Okay, so these are the general types of anisotropic features you can expect in crystals, and you remember these are not constant for everything, right? So it depends on one mineral to another, right? So therefore, we can look for anisotropic properties of different crystals, right? So I will give you an exercise to do as an assignment, right? You have to find out uh, different crystals, and at least you take five crystals. You take five crystals and discuss about their isotropic and anisotropic properties, right? So I will put that in your LMS. But you are given 1 week to submit that, right? You can submit it to the LMS, and it will be counted for continuous assessments, right? So during this holiday time, you can use your time to do this assignment, right? Uh, Isotropic and anisotropic properties of crystals. That is the topic that you have to elaborate, taking five examples, right? Taking five crystals as example, right? Whatever the properties that you are going to discuss is okay as long as they are uh, related with isotropic and anisotropic properties of crystals. We try that. Okay, right. So that is the first assignment that you are going to get under this earth material course. Okay. Do you have any questions? Do you have any questions related to today's content or previous contents? No? All right. So we proceed then. Okay. Right. So we just had an introduction about the crystals, and now I will give you some overall picture about some defects related with crystals, because these defects are important for you to study at your 3,000 level or 4,000 level, because we are dealing much on with the deformations of rocks and minerals, right? So for that, you will need to know about the crystal defects in details, right? But uh, at this level, we will just have a very brief introduction, very kind of illustration only, right? We are not discussing in much details, but this is important, so you have to keep in mind. So these crystal defects are caused by uh, some uh, some uh, some missing atoms or additional atoms or some movements in planes or lines of crystals. Right. So we will see what these defects are. We can define or we can categorize these defects into three categories, right? The first one is point defects, right? These point defects uh, is related with a single atom, right? A single atom uh, in a form of a vacancy. It can be in a form of a vacancy. That means some missing atom in a crystal, right? For example, you can see here uh, in this place, right? In this place, there is no atom there, right? So this atom is missing in that place. So that place is called a vacancy. So such places are there in some crystals, right? This happens actually mainly related with deformation, right? When the crystals are exerted with some external force. That means Earth's interior, there are so many dynamic forces, so cause uh, which cause these crystals to be deformed, right? So that makes some defected crystals. So vacancy is one of those types which we call a point defect, right? It's just a point defect. In addition to that, there can be some additional atoms there in crystals, right? For example, here you see in this place, you can see an abnormal type of a replacement there, right? Uh, that is causing some kind of a bending in the structure, right, in the crystal. So that is the defect, deformation, right? Even in the previous case, the vacancy causes kind of a bending here, right? So that is the defect occurring to the crystal as a whole due to one point defect, right? So sometimes you have some atoms which are not in the proper place, which is not supposed, I mean, it is not supposed to be there, but somehow there can be some uh, substitution there, right? So actually, this type of interstitial atoms coming there can be caused initially by vacancies, right? Once you have a vacancy, there is a kind of a space, right? To fill that space, usually some atoms try to replace it, So once one atom is going there, if it is not fitting, uh, it can just dislocate. It can just go outside and can be there in a low energy place, right? Normally, these are related with thermodynamics as well, right? The energy distribution is also matters. So this type of ones are called self-interstitial. That means the same type of atom is replaced there in a crystal, but not in the proper place. So you can see locally, right? One can notice that, I think local amorphous nature is there, right? So if you take this as a unit cell, you remember the unit cell, the smallest repeating unit in a crystal, right? This is it, right? But I mean, when you have bigger units, I mean, repeating units, if you take this as a repeating unit or this as a repeating unit, you can take, right? Unit cell is the smallest repeating unit, right? So you see this repeating unit, which was available systematically in the previous case, now has been distorted, right? So no longer you can see this repetition, right? Here is different, and here it's again different, right? So locally, the crystal can be uh, converted into an amorphous material because of this type of things. But it doesn't matter. It doesn't mean that the entire crystal is amorphous, right? No, we call it a defected crystal, not an amorphous crystal, amorphous material, right? It's a defected crystal. Still, crystalline feature is there, right? I mean, predominantly. This is not always available. Everywhere it's not available. I mean, it is also not isotropic, right? It is also anisotropic, right? Even dislocations are anisotropic, right? They are not distributed evenly in all directions, right? So because of these vacancies, sometimes these vacancies are filled with a bigger atom, which is not fitting to the structure, right? So in that case, there can be a lot of, large dislocations, like big bending like thing, right? So that may cause some of these planes to be distorted, right? Even the planes, like these are the planes. These planes can be distorted because of big ion replacements, right? Self-interstitial means the same size of a atom is replacing, and if it is replaced by a big ion, then ion or atom, then planar displacement can distortion can be taken place, right? So actually, in this case, just a point dislocation is there, right? So interstitial atoms and substitutional atoms. Substitutional atoms means a bigger atom is coming into the structure, right? Those are substitutional dislocations, right? So these defects are called dislocations also, right? Remember, dislocations. Defects are also called dislocations. But majorly dislocations are actually defined when it is happening as a line or yeah, mainly as a line, right? For example, this line, right? This line is defected. So that's why we can use the term dislocation also there, right? But if the entire line is defected, right, not like one single place like here, right, there can be some more replacements. There can be some more replacements or some more missing ions along a line, a single line, right? So then you can call it a line defect, right? It's not a point defect in that case because it is happening in a linear manner, right? So that is called a line defect. And also it's possible this can happen as an area throughout an area. Actually, normally throughout an area means it should be happening along a plane, entire plane, right? Because these lines, individual lines, makes a plane, right? All these lines collectively make a plane. So if the entire plane is defected, right? So these can be area defects. These can be area defects, but still you can call planar dislocations, right? In the previous case, it's a line dislocation, right? But if it is spread throughout the plane, then you can term it planar dislocations, right? So these planar dislocations sometimes makes the grain boundaries level also, right? So one crystal, for example, in this figure, you can see one crystal is here and another crystal is here, right? For example, in a rock, you can have one crystal, right? Say it's a quartz, right? Uh, Mineral A, and there can be another mineral in line with it, right? So if they are crystalline without any defects, then no problem. So this grain boundary is very stable, right? This grain boundary here in this zone is very stable if there is no dislocation, right? But when you have a dislocation, right, some planar dislocation, like the entire surface like this, having some kind of defects. In that case, this grain boundary becomes a little bit diffused like this, right? It becomes diffused because it's a planar dislocation, so that causes the boundary of those two grains. So it can even cause these grains to be slipped, right? Here you can see a slipping of one line over the other, right? So this line has moved a little bit far compared to the other one, right? And also you can see these two lines are moved relative to the other one, right? So these called slip plane. This makes some new surfaces, right? New surfaces mean this surface, right? This new surface is generated due to this planar defect, right? So this planar defect, which is available at the grain boundary, causes slipping of these atomic lines that causes to generate a new weak plane that we call a slip plane, right? This slip plane generation is also caused by crystallographic defects, right? So when actually the physical conditions, what we call physical conditions, is the pressure and temperature. So this pressure and temperature has a big effect on this, because you know the anisotropy of mineral, the crystals is different with respect to the exerting force also. Okay, you learned it before, right? Along the different crystallographic directions, you have different properties, right? So all these things can contribute in different amounts for generation of a slip plane. Even in a landslide, right? You know, the during the heavy rain, you can have landslides. There are also some slip planes are generated. So all these slip planes related to landslides are a result of weathered feldspars mainly, because they form clay minerals, and clay minerals are very flaky ones, flat type of mineral that can easily slip uh, relative to each other, right? So there, this generation of these slip planes is very easy, right? That happens from the crystallographic scale itself, right? Uh, it happens with the crystallographic scale uh, also, right? So initiation. So therefore, uh, these dislocations and these defects are very important to study in many, they have many applications, right? So you can see some kind of a crystal again, and you see here there has been a dislocation occurred this place. This dislocation makes all other lines to move relative to each other. So you see some kind of movement towards these two directions, whereas some contraction is happening in the middle at the interior, right? So this difference in their property can cause to generate a slip plane, right? this slip plane can uh, create along this region, right? Because you see the other two directions, they are kind of opposite directional movement is there, right? So this type of dislocations are there. We will learn under structural geology about these dislocations in detail, right? So this is a very introductory part of the crystal defects, because under the crystallography you may have and you may encounter some defected crystals also. Therefore, it's important that you learn this one also, right? So, do you have any question? All right. So, we will. We had a preliminary discussion on crystals, right? Crystals and their isotropy and anisotropy and definition and everything we just covered through these lessons during the past weeks, right? So if you have any question, please let me know. And remember, there is an assignment that I already mentioned you. So for those who were not there at that time, you should find out the isotropic and anisotropic features of crystals, uh, taking 5 examples. Okay, so you can make a description or elaboration with the diagram sketches, right? So that will be counted as a continuous assessments, one of the continuous assessments. So please make sure that you upload it by next Monday, right? By midnight of next Monday, you should be submitting it, right? Okay. Right. So we will consider uh, with some illustrations. We will consider about the unit cell again, right? So the unit cell is the smallest unit of repeating uh, in a crystal, right? So you can see here, uh, this is a repeating unit, right? So you have a repeating unit here, because you can have a bigger repeating units also, right? For example, you can take two of these, that is also repeating, right? That is also repeating. So you take one such unit which makes the smallest framework of uh, atoms that is repeating throughout the crystal. Okay, right? So it's a kind of a unit volume actually, right? Identical cells. So uh, each and every unit should be representative of that particular crystal. Each and every crystal unit cell should represent the crystal at anywhere, right? So this repeating pattern or the unit cell goes redundantly over and over in all directions, right? So using that, you can construct the entire crystal lattice, right? So it's kind of a building block, okay? It's a building block of repeating units, actually, right? It's a building block of a crystal. So you can easily construct the crystal using this unit cell. So unit cell is very different in for different crystals. It depends all on the crystal shape. So there are geometric shapes of crystals which we haven't learned yet in detail, but I took some examples before. One is cubic system, right? One is a cubic system. So in this cubic system, you can see everything is arranged in a equidimensional lens, right? So that it in 3D it makes a cube. Okay, right. So this is the unit cell. So that you have to keep in mind, which has a repeating unit, right? So unit cell shapes can be different, as I said before, but the shape and size of a unit cell is very important, right? Shape and size of the unit cell define its symmetry, actually. So symmetry, the general meaning of symmetry. The symmetry is important for crystallography. So what do you mean by symmetry? What kind of symmetries can be there? So these are important for crystallography, right? So you take a cube, or you take a cube first of all, right? So you take a cube and you turn it to different directions, right? So say you can turn it to upside down or leftward or rightward. You can rotate, right? Wherever, or I mean, which direction you rotated it or turned it, you will see still the cube is in the cubic shape, right? You don't see any different shape. You don't see any other shape from the cube, right? You never see the cube with a kind of rounded edges or something, right? No, cube is cube in all directions. So that means it has a symmetry. Symmetry means in all the orientations, or at given orientations, rather, because for some crystals you don't see that property. Cubic system for the cubes, or the crystals that belongs to the cubic system will have symmetries in all directions, very in a defined way, right? It is distributed as an isotropic property there, right? So anyway, shape and size of a unit cell is important. That gives you a point symmetry, because the smallest unit, being the smallest unit, you can take it as a point, right? You can take it as a point of the building block. So you keep these blocks one by one, so that there is no space in between. That is also important. You can't have any space in between. So that's how you have to select the unit cell also. Sometimes you can select the smallest unit, but when you pack it in the 3D-dimensional space, there are some empty areas in between. So then that's a problem, right? So you cannot take it as a unit cell. So you have to take the unit cell so that it makes all packing without any space in between, right? Hollow space in between, right? So shape and size is important, as we define it point symmetry. And the other one is location of the lattice points. Location of the lattice points is also important for this unit cell. That means there is a special term called translational symmetry. We will learn about that later on. First, the shape and size that you can easily understand. uh, Shape and size of the unit cell is important, and the other one is the location of the lattice point. So you see the lattice points. These are the lattice points, right? These are lattice points. One point is here, another point is here, another point is here, another point here, here, and also here, right? The middle is also a lattice point, right? You can have these different lattice points, right? So this lattice point, the location of relative location of these lattice points is also important for a cube. When you take a cube, you see the location of lattice points are very equal everywhere, right? You take a ruler and measure if this is big enough, right? Let's assume this is big, unit cell is big, then you can measure, right? So one point is here, another point is here, so you measure this distance, okay, 1 centimeter, let's say, and you measure the other side also, that should also be 1 centimeter, right? And this direction, y direction, x y z direction, sorry, this is z direction, right? There also the distance should be 1 centimeter, right? So like that, the uh, the location of the lattice point should also be uh, constant. So that is called the translational symmetry. So the previous, the shape and size gives you the point symmetry. That means whenever you rotate or you rotate or you visualize it in different directions, you must see that in a constant shape, right? That is point symmetry. But the distance of each point should be also be constant, and that gives you translational symmetry, right? So this is a single unit cell, but suppose that you have another unit cell here, right? So for the translational symmetry, the length or the distances should be equal, right? So when you put another unit cell here, I said you have to stack these unit cells without keeping any space, extra space in between, right? So if you pack it perfectly, right? So the distance between this point and the next point of the next unit cell should also be constant as 1 centimeter, as we said before, as the example, right? So that means uh, even if you move your unit cell in one unit this way, right? If you move your unit cell in one unit, for example, 1 centimeter, in one direction, you must be able to transpose the other unit cell, right? You cannot see any offset in between. The distance should be equal. So that is what you call the translational symmetry. So point symmetry and translational symmetry are two important types of symmetries that are important for us to define different crystals. Okay, right. So we have to learn about these different types of symmetries and how these symmetries are produced, that we call the symmetry operations, right? So these symmetry operations we have to do in detail, and I will do that in the next, giving some examples. I will show you more details about this symmetry in the next lecture. Okay, right. So up to now we have learned the crystal uh, shapes and their systematic units and unit cell and their symmetries, basic definitions of the two types of symmetries that we can describe, right? Any question? Do you have any question? All right. So if you don't have any questions, so we can stop here for today. So we will meet with more details on the symmetries from the next lecture, right? Tomorrow. Okay. Have a nice time.